So we're going to continue our discussion of bonding, this time talking about ionic compounds and ionic bonding. So let's talk about stable compounds. So atoms in a stable compound have what's called a noble gas arrangement of electrons, meaning that their outer shell is full. So they will lose or gain electrons in order to have that. So nonmetallic elements will achieve noble gas electron configuration in two ways, either by forming covalent bonds, sharing electrons with other nonmetals, or forming ionic bonds where electrons are taken from representative group metals. And so for a covalent compound, electrons get shared so that the valence electron configurations are completed or the outer shell is full for both atoms. Or, half full, where we talked about like the D being half full. For an ionic compounds, electrons are stolen so that the valence electron configurations are complete. So the metal will give up the electrons and the nonmetal will take them. So we can use those things to predict formulas of ionic compounds. So ionic compounds are assumed to be in the solid state. This means that they are closer together. The atoms are closer together, and this maximizes the electron-proton attractions and minimizes the proton-proton and electron-electron repulsions. So, for example, if we look at calcium, calcium's electron configuration is argon 4s2. Oxygen's electron configuration is 1s2, 2s2, 2p4. Oxygen has a larger electronegativity value, and this is also a metal and a nonmetal, and so the nonmetal, oxygen, will steal the electrons from calcium, the metal. Now, to figure out how many electrons are going to be stolen, we want to use noble gas configurations because that's the stable configuration. So for calcium, it wants to be similar in electron configuration to argon. It doesn't become argon, its electron configuration is similar. And so if it gives up 2 electrons, it will achieve argon's electron configuration. Oxygen will achieve neon's electron configuration if it takes in 2 electrons, making it 1s2, 2s2, 2p6, which is neon's electron configuration. And so because calcium wants to give up 2 electrons, it will form Ca2 plus ion, and because oxygen wants to gain 2 electrons, it will form the O2 minus ion. And so when we put those together, we have a 1-to-1 ratio, and so the compound becomes CaO, or calcium oxide. So let's take a look at an example. So I predict the ionic compound formed between aluminum and oxygen. Oops. Okay, so for aluminum, first let's write the electron configuration. So that's neon, using our shortcut noble gas, 3s2, 3p1. And for oxygen, 1s2, 2s2, 2p4. We already talked about how oxygen wants to gain 2 electrons, making it O2 minus. Now, if we look at aluminum, if it loses these 3 valence electrons, it'll have electron configuration similar to neon, and so it will lose 3 electrons. That's going to make it more stable, making the ion Al3+. So then if we put these together, we know we need 2 aluminums and 3 oxygens in order to have Al2O3, and that's our ionic compound. So we know that groups exhibit common chemical properties because of their valence electron configuration. All elements in a group have the same valence electron configuration. So we can use that to help us figure out the ion charges. All of group 1A is going to have a 1 plus ion. All of group 2A is a 2 plus ion. Group 3A, so we're skipping over the transition metals, going to aluminum's group, they're going to be 3 plus ions. Then if we have 6A is the 2 minus ions. Group 7A is the 1 minus ions. Those are our halogens. The only exceptions to this would be tin, lead, bismuth, and thallium. They can have a few more different charges than what we follow normally for the groups. And remember, this only applies to representative elements. Transition metals are a different story, and we'll talk about those more later on. So let's also use this periodic table to talk about the size of ions. Size of ions is important in the structure and stability of ionic solids. It's also important in their properties of ions in solution and also in some biologic effects. So cations are going to be smaller than the parent atom. Because they are losing electrons, they become smaller. Anions are the opposite. They become larger than the parent atom. Parent atom we consider to be the neutral atom. Okay, and so anions are larger because electrons are added. And then we're also going to use the same trend as atomic size. Ion size increases as you go down a group, mainly due to that increase in atomic size. We're adding more protons, we're increasing the number of energy levels, it's just getting larger in general. So we have a new vocab term, which is isoelectronic ions. So these are ions that contain the same number of electrons. So for example, O2 minus, F1 minus, Na plus, Mg2 plus, and Al3 plus all contain the same number of electrons. Now they all have different numbers of protons because they are different elements, but their electrons are all the same. And in fact, it comes out to 10 electrons per ion. Okay, there are two facts to consider when we predict size. First, you have to consider the number of electrons. Now, if it's the same, as in, for our example, if all the elements or ions, rather, are isoelectronic, then there's no effect. And so then you have to go and look at the number of protons. So for our example, the number of protons increases from 8 for oxygen to 13 for aluminum, and size will decrease as nuclear charge, which is equal to the number of protons, increases. And the reason for that is because the more protons you have, the stronger the attraction on those electrons, or the more the pull, and so it's going to pull it in really tight and small, making it smaller. And so in this case, we would say that oxygen is the largest and aluminum is the smallest. Same number of electrons, so when we look at protons, aluminum has 13, and those are creating more of a pull on the electrons. So let's look at an example. So we want to arrange these ions in order of decreasing size. So if we look at selenium and 2 minus, so if we take selenium and move and do the electron configuration with those additional 2 electrons, its electron configuration is similar to krypton. And krypton, or selenium in this case, would have 36 electrons. Now, selenium has 34 protons. And remember, that's not going to change whether it's an ion or not. So now let's look at bromine. Well, if we add 1 electron to its electron configuration, it also comes out to be krypton. So it has 36 electrons, but has 35 protons. Okay, if we do rubidium, again, we take away 1 electron from its electron configuration. It's similar in electron configuration to krypton. It's got 36 electrons as that ion, and it has 36 protons. And then if we look at strontium, if we take 2 electrons away, again, its electron configuration is similar to krypton, meaning it has 36 electrons and 37 protons. So these are isoelectronic. So now we need to look at the number of protons. Because strontium has the most protons, those are going to pull the most on the electrons, pulling them in, making strontium our smallest ion, which then makes selenium our largest. And so if we were listing them in order of decreasing size, we would go selenium is greater than bromine, which is larger than rubidium, which is larger than strontium. Okay, so now we want to choose the largest ion in each of the following groups. So let's put both examples. So we're going to look at example 1 first. Lithium, sodium, potassium, rubidium, and cesium. Well, lithium has 3 protons, and because it lost 1, 2 electrons. Sodium has 11 protons and 10 electrons. The potassium ion has 19 protons, 18 electrons. The rubidium ion has 37 protons, 38 electrons. And the cesium ion has 55 protons, 54 electrons. So these are not isoelectronic. And as we're increasing the number of electrons and increasing the number of protons, remember, as we go down a group, size increases. And so cesium would be our largest ion. So now if we look at our second example, barium has 56 protons, and because it lost 2, it has 54 electrons. Cesium has 55 protons, but because it lost 1, it has 54 electrons. Iodine has 53 protons and 54 electrons. And then tellurium has 52 protons, and because it gained 2, has 54 electrons. So these are what we consider isoelectronic. Because barium has the largest nuclear charge, it is the smallest, and so that makes tellurium our largest ion of those 4. Okay, so now let's talk about some energy effects involved with ionic compounds. The main thing we're going to talk about is lattice energy. So the change in energy, this is the change in energy that takes place when separated gaseous ions are packed together to form an ionic solid. Okay, so we're taking ions by themselves and we're making them into a compound or an ionic solid. Energy is released when an ionic solid forms, so that makes it exothermic, and so it has a negative sign. And so let's look at an example. So this is what we're trying to do, is take our gaseous and form our lithium fluoride. So first we're going to sublimate the solid directly into a gas. Then we're going to ionize those atoms to become ions. And again, you can see this is all endothermic so far. Then we're going to dissociate the F2, we're breaking it apart. Okay, and then we're forming ions from those neutral elements. And here you can see this is exothermic. And then we're going to take those ions and put them together to form solid lithium fluoride. Okay, and so if we add all those up, we end up with a delta H of negative 617 kilojoules per mole, showing that it's exothermic. Okay, and so this is a large negative lattice energy. So energy released when an electron is added to fluorine is not enough to remove an electron from lithium. So those energy exchanges aren't the same. If that was all the energy we have, this would be an endothermic process, which wouldn't be favored. And so what this means is that the main reason for formation of an ionic compound, rather than forming a covalent compound, is the attraction between the lithium plus and the fluorine minus in the solid. So they really want to be attracted that way, and so they're going to form an ionic compound versus forming a covalent compound. And the energy, because it's exothermic, helps to prove that point, because that's what's going to be favored. So lattice energy here is the dominant energy term. So if we take a look at other ionic compound structures like sodium chloride, this is the common structure for most alkali metals and halogens, and it's arranged in order to maximize that attraction of protons and electrons, but minimize the repulsions of proton-proton and electron-electron. And so let's take a look at that formation. And so here we've got our large chlorine ions and our small sodium ions, and you can tell it's a crystalline structure. They are arranged so that sodiums are not next to each other, okay, but yet chlorines and sodiums are close. Now you've got some chlorine here, but we've got this very strong attraction between chlorine and sodium. Okay, we can also calculate lattice energy. So here's our formula, or our equation. And so if you want to write it so it's not in horizontal form, Q1 times Q2 over R. And we have talked about this a little bit already. K is a proportionality constant, depends on the structure of the solid and the electron configurations of the ions. Q1 and Q2 are the charges on the ions, so for sodium chloride it would be +1 and -1. And R is the shortest distance between the centers of the cations and anions. So if we had chlorine and sodium, here's the center, and then we're measuring that distance. Lattice energy is negative when Q1 and Q2 are opposite signs. Okay, so because forming that ionic compound, bringing cations and anions together, is an exothermic process, and so it's going to be negative. Lattice energy can be gained in going from singly charged to doubly charged ions. So magnesium oxide is a +2, -2. And so that's going to help gain some lattice energy. So sodium fluoride isn't doubly charged because they both have a neon electron configuration, so being +1, -1 makes them more stable. Okay, so before we get to your checks for understanding, I thought you would enjoy a chemistry cat joke. So I'll let you take this in for a minute. Pause if you would like to enjoy it for longer. And so let's go to our checks for understanding. Okay, so in this section we talked about ionic bonds and ionic compounds. So number 1, what arrangement of electrons makes atoms stable? And describe the 2 ways that nonmetallic atoms accomplish this or become stable. Number 2, predict the ionic compound formed between lithium and bromine and justify your answer using electron configuration. Number 3, arrange these ions in order of increasing size. So sulfur, potassium, chlorine, and calcium. Are any of these ions isoelectronic, and how do you know that? Number 4, is bond formation in an ionic compound exothermic or endothermic, and which of these is a favored process? Number 5, what is neat about the structure of an ionic compound? So, i.e., how are the cations and anions arranged? And number 6, what is the equation for lattice energy? So please make your best effort at these, and we'll discuss them in class. Have a good day.